Hello, I am Professor Stephen Abbott. My book, Adhesion Science, Principles and Practice, is linked to a large series of apps on my Practical Adhesion website. In this video, we look at apps that use the powerful JKR methodology to show where strong adhesion might be found. We've seen that surface energy is not at all important for adhesion. I want to explore the JKR method for thinking about real adhesion, and I have to start with the Hertzian contact, where there is absolutely no adhesion whatsoever. You have a sphere of radius r, it has a modulus E, and it's being pushed with a force F against a surface. And the contact width A is given by this Hertzian formula. When I have no force, obviously the contact width is 0. When I increase the force, the contact width increases. All very straightforward. If you do that with a real surface, then when you have 0 force, you actually have a contact width, in this particular example, 412 microns. And that width A is calculated by this formula, which is the famous Jkr formula, named after Johnson, Kendall and Roberts. Who cares? Well, this formula depends on the surface energy, and as you change the force and measure the width, you can fit this formula and extract from it the surface energy. So this is a great way to measure the surface energy of any material. And you then get a Jkr curve. So this curve here is the Hertzian curve, so at 0 force you have 0 contact width, but this is the typical curve you would get with a JKR experiment of pure surface energy. If I increase the surface energy, then of course the JKR curve gets bigger, and in particular you have to go to a negative force to pull it away. So I need minus 10 millinewtons to pull it off when the surface energy is that. When it's low, I need minus 5 or something like that, minus 4. So from this JKR curve, you can start to get to know the pure surface energy. But as I said, surface energy is of no interest to adhesion. Well, it turns out that when you do these experiments for real, you don't get a simple JKR curve. And this is because intermingling starts to help with this. What happens is that this is the standard JKR curve, but if you actually do the experiment, then this is what you would see during loading, which is the standard JKR curve. At 0 force, you still have a contact width of 400 microns. I've kept the same material. But if you wait a moment and unload, you find a curve like this. And you have now to go to minus 60 or minus 70 millinewtons before it pops off. And the measured surface energy, the measured effective energy, is now 0.4 joules per meter squared, not the 0.04. So we've got 10 times more. And it's coming because I've got a density of polymer chains, about 1 per each nanometer squared, and they intermingle by about 1 nanometer. If I intermingle more, then I get more effective surface force. I get more intermingled adhesion. And in the big overview, I say that you can get about 1 joule per meter squared from intermingling, and that's where this number comes from. For those who want the formula, it's the famous Dejenne Formula, sigma nu, the density, the number of polymer units, and a friction coefficient, which is 3.5 kilojoules per mole. So that's what would happen if you had an intermingled system. If you had a real system where you had entanglement, we still have the same formula. The work of adhesion is sigma nu, but this is now much more to do with entanglement, and that's described at length in this app. But I want to show you the effect of this. When I start having a nanometer of entangled interactions, there's the loading curve, and here's the unloading curve, and we've now got 30 joules per meter squared. So if you could do this JKR experiment, then you would find an amazing difference between the loading and unloading curve, and that's the entanglement. An entanglement is shown here. If I have a polymer chain and an interface, if it crosses that interface 3 times, where the stars are, then it's entangled, and if it only crossed 2 times, if you broke the chain here, it would be unentangled. If you broke it here and you pulled up on this point, then it would just pull straight out. If it's not broken here, if it's really like this, if I pull up here, then of course this loop here is going to tangle with something there. It sounds a very simple definition of entanglement. It's a true, really good physics effect. So we've gone from no adhesion, the Hertzian formula, we've used the JKR technique, and now we find that this has led us to be able to analyze quite strong adhesion with entanglement.